this FDP, and welcome to all the participants. So this is I understand this FDP is about malware analysis. So malware is a big threat to our cybersecurity. There are many ways we get infected by malware, even on our phones and our even in other devices such as devices like network devices and devices that are used in the industrial control system and so on. So now ransomware is a very specific kind of malware. And since I am talking before you are actually getting basic introduction to how malware analysis is done and so on. So this might be a little bit putting the cart before the horse kind of situation. But I will try to explain to you as simply as possible so that you understand what exactly is being done for ransomware detection and prevention. So it's not only just detection, because detection can may be too late, and by then the ransomware may actually have encrypted most of your files or data, and thereby it's too late to know that you are affected by ransomware. Because in any case, if ransomware encrypts your file system, then you would know that you are affected by ransomware. So that's the detection itself, but such a detection is not of much help. So we need to actually prevent the ransomware from executing either from the very beginning or at least very early on, so that we can save as many files as possible. Now this is something that has many aspects of malware analysis and many aspects of trying to detect which processes are involved in the process of encrypting, and then about killing those processes in time, right? So that's what the prevention would be about. So let's see. So what we want to do is that we want to understand what ransomware is and how the detection and classification works. Ransomware is also of not one kind, right? So there are many different kinds of ransomware. They have different characteristics and so on. So you may want to also know which ransomware is affecting you, and then that's what classification is about. Now there are many ways to do this. So one thing in any malware analysis, we want to get the features when any binary or any executable executes on your system. It uses various things, right? So it might make API calls. It may actually invoke certain system libraries. It may actually create new files. It may delete files. It may actually make changes in Windows registry. It may actually behave differently with respect to CPU usage, network bandwidth usage, memory usage, and so on. So anytime an executable is observed executing on your machine, you can actually note down all these aspects of that execution, like how much CPU is being used, how much memory is being used, how much on an average or at the peak. You may want to measure these things. You may want to measure what API calls are being made. You may want to measure what libraries are being loaded. You may want to see how many files are being created, whether any file is being read. You may want to know whether some registry entries are being created or updated or things like that. All those things are kind of indicators of that particular executable, right? When every time that executable executes, you may expect that all those things to happen. So therefore, these indicators may be used as features if you want to characterize the executable. If that executable has these characteristics. So one of these important characteristic is API call analysis, because depending on what kind of malware is executing in your system, the API calls will be different. And therefore, API call analysis was one of the first things that people thought about when they started thinking about how to detect malware or how to classify malware. So in ransomware also, there are certain API calls that are more often called by ransomware, which are not so often called by benign executables or normal executables or by other classes of malware. So that is something that one has to check whether there's certain API calls are being made by your by whatever is executing on your system. And if you see too many of those API calls, you might try to figure out that something is wrong. Then API calls do not always work. We'll talk about that, why API call based analysis may not always work, because malware creators, they also know that we are trying to detect them through APIs. So what they would do is that they would do direct system calls instead of engaging APIs. So any method that depends on API call analysis will not be able to detect ransomware which is not using the API calls but using direct system calls. So therefore, there could be other ways to detect it. One such way is to actually look at the performance registers in hardware. So Intel based hardware, they have this registers which count various kinds of events, system events, and these events counts will be vary from one malware to another or one executable to another. And then if you find that certain classes of ransomware gives a certain kinds of counts in these registers, then you can actually use them as features to characterize the ransomware. And then finally, you can also do this by looking at what kind of registry modifications, registry activities are being used by the executable. And then you can also you may also want to know which of the processes right now that are running on your system are doing this ransomware activities. It's usually not a single process, but multiple processes. So you have to look at the root of the process tree. And then if you can kill the root of the process tree in a very quick time frame, then you may actually stop the ransomware from actually successfully encrypting your entire file system. So that's what we do in the RANDART. That is the last thing that we want to talk about. And then we'll talk about some of the conclusion and future work. So all of you probably know that the crypto ransomware is the malware that encrypts your file system, encrypts your data, and thereby stop you from using your own data or your own machine. And we also know that ransomware, if you read any threat report of today, you'll find ransomware is in the top 5. Top 5, the attacks that people are facing every year. A ransomware is at a very high level of at the very high rank in terms of the kind of threats that are still going on in this space. At the cost of ransomware, cost of even if you don't pay the ransom, you may not pay the ransom because you may have the backups of your data and so on. But even then, it's a lot of expensive because you have to clean up your entire system. You have to rebuild your system. And also in the time that you are encrypted, you lose business. So average cost of ransomware incident is about $1.85 million per incident. That was in 2023. It may be slightly more now with inflation and so on, but let's say 2 million. But per incident, 2 million is a lot of money. The other problem is that now the ransomware has become multiple variants, and these variants can actually do things very, very quickly. So, for example, in 4.5 minutes, this particular variant can encrypt, um, uh, 22 so 2 lakh 20,000 files in about less than 5 minutes, right? So if your file system has less files than that, then unless you can do something, you can do intervention very quickly, you are going to lose your file system. And then there is another thing called double extortion. In the double extortion, what happens is that they actually steal your data first and then encrypt it, and thereby the you have to pay the ransom, because even if you have backup, you do not want your customer data, etc., to go out, and therefore you will pay to get your data suppressed. So that's the double extortion problem that is also happening very quickly. So in either case, if you can detect that your ransomware is actually starting to work on your system, if you can detect it very, very quickly and can quickly kill the processes, that would be our goal to protect ourselves from ransomware. So ransomwares have many different characteristics. Sometimes they actually, like many malware, they actually create persistence into the affected system. So they do not want that if you reboot the system, then the malware will go away because it's only memory resident, or it doesn't want that if you actually even rebuild your system, and even then it will be it will be removed. They don't want that. So they try to create persistence by writing themselves in boot sector, or writing them in the startup directory, or create a task which is scheduled, and every time you reboot it will come back up, this kind of stuff. So they create persistence. They also try to do a privilege escalation to get the administrative privileges. So they perform, and this is required by them to actually delete things like shadow copies, master boot records, and stuff like that. They also do not see, one way to detect ransomware was that ransomwares usually have to communicate the back to their command and control servers. So if you know the command and control server IP address or command and control server domain name, then if you see in your network, DNS or other type of traffic using that particular domain name, etc., you could have detected that you are now being affected by ransomware. So in order to avoid that, they actually also do dynamic generation of domain name. So they are not using, standard like a domain name that from before the previous incident, because domain names are generated dynamically. So there are techniques called flux, IP flux, or various kinds of flux techniques that they use. Then, of course, they try to turn off the anti-malware engines, or they execute from application data directory, or they often hijack existing processes and inject code in the existing processes and stuff like that. So therefore, they actually get, try to avoid detection. So that is evasion techniques. And then they also gather a lot of information about the system and try to see if they are being run in a sandbox environment. Like they don't want to be executed in a virtual environment like Cuckoo, Sandbox, and so on, because if that happens, then basically somebody is analyzing them. So that virtualization or anti-sandbox properties are also there in many ransomware. So first thing we want to quickly talk about is the API call analysis. Now, as I said, that different malware, depending on what their goal is, what they are trying to do, like there are many types of malware, right? Like you have ransomware is only one type of malware. You can have Trojans, you can have backdoors, you can have, various kinds of malware. And this malware, depending on what they try to do, they would have to do those things. Like, for example, if you are going to encrypt files, then probably encryption, decryption related API calls, or file read-write type of API calls will be used. Whereas if it is a Trojan, it may not use any encryption, or it may not use any file writing and things like that. So you can do analysis of the API calls to know whether you are dealing with a ransomware. Now, there are two ways to do analysis of any binary. One is called dynamic analysis, another is static analysis. In dynamic analysis, you execute the malware in a sandbox environment, in an experimental environment, and figure out what API calls are being done, what kind of files are being created, what kind of network communications are being made. You capture those in order to characterize that particular executable. In static analysis, you do not execute the malware. You actually look at the binary, look at its metadata, try to extract information like strings from the body of the binary and so on. And then you actually use those information to characterize the binary. Now, so what we did, so this is several years ago, around 2021, I think, that we said, okay, let's see let's look at all the different ransomware families, and let's see what kind of API calls they make. And then we identified about 135 API calls that are pretty common across multiple different ransomware families. And then you can actually also see which ones are most frequently called, right? So some of them are more frequently called than the others. So we took 653 executable files for this experiment, out of which almost half of them were benign, because you have to always compare the malware's characteristics against the non-malware, that is benign executables characteristics, because otherwise how do you know that this is a characteristic of the malware? It may be that all binaries do the same thing, right? So in order to contrast that the malware ransomware uses this particular type of API calls more, and therefore if I see these API calls being called more, I can kind of start suspecting that this is a malware, this is a ransomware. I need to know whether benign files also have the same characteristics. So that's why we need almost half and half, like benign and ransomware samples. And then we found that, like this list of things that we are showing here, the NT-write file, set file pointer, NT-create file, this kind of stuff, NT-create virtual memory. These are some of the common things that we found in this ransomware samples. So these are like these 7, for example, are most invoked API calls. We'll not go into the details of these, but you can see at a very quick glance, you can tell that these are mostly related to creation of files, or reading from the files, or creating new space for doing some like new memory space and so on. So this is all the kind of things that ransomware needs to do in order to do the entire process of creating encrypted files. So here is a picture of the frequency of API calls for these 100 top 50 API calls. And you can see that some of them are at a very high frequency, but many of them at a less than 200, 300, like that. But there are things which are having a frequency of up to 4,000. And when I say frequency, frequency will depend on how long you ran the binary. So therefore, a fixed, for running each binary for that long, you have to see how many times these APIs are being called. And then you have to see whether the same APIs are called by a wide variety of benign files. If the benign files do not call these same APIs, or at least at such high frequency, then you can do the contrast. Otherwise, the contrast will not work. So certain families also have slightly different way of doing things. Like, for example, Avos Locker is a ransomware family. We found that they have a very high frequency of read-write operations on files, whereas Lockbit 2, it was more on a memory-based operations, and Conti had more file-based operations and almost negligible memory-based API calls. So not only can you distinguish use by observing this API call frequencies and especially focusing on this top 50 or top 100 API calls, you cannot you can distinguish between ransomware versus benign. You can also distinguish between different families of ransomware by observing this kind of things. So this kind of shows the call frequency of different types of different families of ransomware. So now, how do you know which are the most distinguishing API calls? And for that, there are feature importance methods. So those of you who are familiar with um, uh, machine learning, supervised machine learning, you know that we often try to figure out, we do not, what features are the most important. So there are many ways to do that. Like you can actually look at the, information gain and various other techniques. So we actually used various feature importance methods. And then accordingly, we decided which of the API calls are the most distinguishing. So in static analysis, we found 180 function calls or API calls, which we found most important. But as you know, static analysis often gives you overestimation because in static analysis we do not know whether a particular API is going to be called at all because it's static. We haven't executed it. Maybe it's in a path that will not be even taken. A particular API call may be in a path that is not even taken. So in case of dynamic, you have a better idea. So we got 135 features from dynamic and 180 features from static, and we combine them, and then based on the data we had, the accuracies were good, the specificity was good, and so on. But as I earlier said, that the API call frequency analysis can only happen if there are API calls. Now, modern ransomware, the creators of the ransomware, they know that people have started using API calls, frequency of API calls as a measure or indicator of presence of ransomware, and therefore they stop using API calls and they are doing direct system calls, and therefore we cannot depend on API calls to detect the ransomware. Second is that they are doing very fast encryption, and therefore we need to actually detect much faster than we can actually wait for API calls to unfold and measure their frequency and so on. And then, of course, generalizability is a problem. If you are depending on API calls in your model and APIs are not being used or in such large number, then you have a generalization problem. So the second thing that we started looking at is if they are not using API calls, what else can give us indicators that can distinguish the behavior of ransomware from regular benign or other type of binaries. So HPC counters turns out to be something that actually turns out to be something where the distinction is visible. So for example, HPCs, there are multiple HPCs and they track, for example, various hardware events like how instruction retirement, processor clock cycles. They often measure some software events such as context switches, page faults, and so on. So there, this HPC counter or HPC hardware performance counters, if we observe them as ransomware executes versus if we observe them as regular executables execute, if we see a marked difference between the values that come up in the HPCs after some time, then we can use that as an indicator, right? So that was the idea. So this is the kind of the experimental setup that was created for measuring this HPC by running the both the benign and the ransomware samples. Of course, this was done in a sandbox because otherwise we would have to buy a lot of hardware, because every time you run a ransomware, especially this ones, some of them actually make it very, very difficult to reinitiate the entire system back to a normal system. Whereas in case of a sandbox, that is Cuckoo Sandbox or other sandboxes, you can basically create, easily do a clean slate. And that's why we use sandboxing environment. So this is how the HPC information was collected. Here is a parf command that was used. So we had a data set of 27 ransomware families with 183 ransomware samples and similar number of benign samples from the software informer. And we did this, and we looked at this 9 different HPC registers. So there are, so actually we found there are about 10 HPC registers, but old AMD and Intel CPUs have only 6. Now again, we actually collected the measures in these HPC counters, and then we actually collected the values of these HPC counters after, let's say, 3 seconds, or after 5 seconds, or after 1 second. And then we actually collected them every 100 millisecond or every 500 millisecond and so on. So every reading that we got of these HPC registers was considered a feature. So suppose I execute a particular binary, and let's say I take the HPC measures for all the registers every 100 millisecond, right? So every 100 millisecond, then in a second, I will have 10 such readings. And then in 2 seconds, I will have 20 such readings. In 3 seconds, I'll have 30 such readings. So for that particular malware executable, I will have a feature vector of size 30. The readings of this HPC registers every 100 millisecond for, let's say, 3 seconds. So I'll have 30, a vector of length 30. If I do it for 5 seconds, I will have a vector of length 50. But if I measure only every second, then I will have, in a 5 seconds, I will have a feature vector of length 5, right? So that's the way we actually try to see what kind of features I can use in an effective way. So this is showing that different variants of this experiment. And as you can see that if I take measurement only once in 5 seconds, and then use that as a way to classify or distinguish between ransomware and benign, then my accuracy is, at the best, I'm getting about 75%. But if I take every 100 millisecond, then I'm getting accuracy of about, I would say, 93%. If you take every 500 millisecond also, I'm getting about the same kind of thing. So total duration of HPC capture 5 seconds seems to be good, and the amount of time between two captures, it seems 100 millisecond is a good number. So that's what we actually decided, that 100 millisecond interval, 5 seconds, I will do. Now if I wait for 5 seconds, some ransomware can actually do a lot of damage by then, right? So I may have to do this even faster. So we looked at 3 seconds. Now in 3 seconds, as you can see that with 100 millisecond, we are getting about 90% accuracy. So I can get shorter duration with a little bit of loss of accuracy, but I need to do this faster, because even in 2 seconds, some of the ransomware families, they actually can do a lot of file encryption, lot of damage. So you have to decide on that. So best results was 100 millisecond intervals. Total duration is set to 2 seconds. HPC register count was also, we took only the most important HPC registers through Boruta feature importance methods, and then we got this 5 HPC registers. Now we also looked at some of the wiper malware. Now wiper malware is similar to ransomware, but it is slightly different in the sense that instead of encrypting your data, they erase your data. So they come in and then they erase your data. Now, if you do not have backup, it is as bad as ransomware, because you lose your data, right? So we look at the various wiper ransomware samples from the Ukrainian wartime, and we found that they have different with respect to HPC register. Their behavior is quite different. So we can distinguish through HPC register based features the difference between the wiper malware versus the ransomware. Now, HPC registers, as you can see, is taking about 2 minimum or 3 seconds before we can actually give a give a verdict that what is happening now in your system is a ransomware. And then I also have a problem that in 2 seconds, some ransomware can actually do a lot of damage. As you can see, Logbit encrypts 25,000 files per minute. So which means that per second, it would be about 4,000 files. So in 2 seconds, it will get already 8,000, 9,000 files. Now, Rorschach actually can do even worse. It has about 8,000 files per second. So it can, if I wait 2 seconds, I lose about 16,000 files. Avos Locker is starts 200 parallel threads, which means even faster. So you can see a screenshot from a running of an Avos Locker. You see the number of threads is 200. So therefore, I need to be in a hurry to even detect and do something about it. So it's not only just detecting post facto that, I have detected that I have been, affected by a ransomware. I need to detect it maybe in couple of, in a second or less than, second. And then I have to also kill the process or the process tree that is involved in doing all this, right? So that is the third thing I want to talk about. So we looked at this API call method, hardware performance counter method. We also looked at, we haven't looked at, in this talk, but one can also look at the way the ransomwares affect the Windows registry versus a benign executable does anything with respect to Windows registry. So we can actually use that as for some features. People have done that. And then trap files. So trap files are files that are instrumented files that you intentionally put in your system. So when your ransomware starts to encrypt files, as soon as it starts to do that to a trap file, the trap will create an alert, right? And that's how you know that you are being encrypted. Your system is being encrypted. The only challenge in trap files is that ransomware may actually start encrypting files from a particular directory, maybe the top level directory, maybe the most deepest level of directory, and so on. So if you put your trap file in a directory, that will be that the ransomware will come very late to detect, to encrypt, then you will also detect the ransomware very late. So therefore, it is very difficult to figure out where to put the trap file, or should I put many trap files? The problem with the many trap files is that if you put a lot of trap files, then sooner or later, users will start getting into the trap files, and then they will be generating alerts, which will be false alerts. So you cannot like have trap files all over the place. That will be kind of like a landmine kind of situation. So you have to be very economic about use of trap files, but you have to maximize the probability that the ransomware will come to the trap file faster than if you just put in an unplanned manner some trap files, right? So that's the challenge of trap files. So Windows registry, we talked about the API calls to see what the whether a certain types of API calls and are being called in high frequency, then you can detect ransomware. If API calls don't work, you can actually look at the HPC registers, take their measurements, and then you can use that for detecting whether you are being affected by ransomware. The other thing you can look at is that Windows registry, what kind of things ransomwares do to Windows registry. If Windows ransomware, of course, it won't work in the Linux and other type of environment. But here, if you do this Windows registry ransomware, then you can see that early signs. There are multiple early signs like deleting shadow copies, employing restart manager to turn off antivirus applications, adding a run key into the registry, introducing new file extensions, executing extensive file search operations, and this kind of stuff. So therefore, I can create a similar feature set that if these things happen, I will try to see whether these things happen more often on this versus more often on that, in case of ransomware versus on benign, and then you can create a distinguisher. So here, for example, there are various kind of registry categories in Windows that we have found that are affected by ransomware variants, not so much by normal software, normal binaries. So using that, you can actually build a detection method. There are two ways to do that. If you study the entire behaviors of ransomware families with respect to registry, you can either create some rules. You do not necessarily have to do this with machine learning. You can actually create some rules that if I see this things happening, I should generate an alert. Or you can actually say that I'm gonna see this as I will also use the trap files. So if I can put the trap files and then I use both the information. So I try to see whether the registry information is telling me anything about with that some anomalies are detected in the registry, as well as I am getting a trap file being read and being encrypted at the same time. Then I know I can be very sure that this is happening. And also, I can detect which process is actually doing this to the trap file, and then look at this process tree, go all the way up to the root of the process tree, and suspend the processes, and then consult the registry-based method, which may be slower. So trap files, you may encounter the trap file first. So if the trap file has been touched, then you are kind of sure that you are dealing with a ransomware. So what you do is that you detect the process that is involved in dealing with the trap file. and then look at the process tree, and then look at the root of the process tree, and suspend the entire process tree immediately. So you are not killing the process tree immediately because you want a second factor, that is the registry-based method, to tell you that indeed this trap file, whatever is affecting the trap file, I am getting the second opinion from the registry-based method that it is an indicator of ransomware, and therefore I am now after suspension, after getting the second opinion from the registry-based method, I can kill the entire process tree. But before that, don't kill the process tree, because if you do that, and if it is not corroborated by the registry-based method, maybe some user by mistake opened a trap file. And therefore, doing something drastic will not be good idea. So that's the idea of, and we call this particular tool called RANDART. It has been also patented. So now the question is, how do you detect, how do you decide where to put the trap files? So by observing various ransomware families, we found that some ransomware families starts encrypting in a breadth first manner, the directory hierarchy. Directory, you can think of the directory hierarchy as a tree, right? So some ransomware do it in breadth first manner, some does it in depth first manner, some do it in the file name order, that is the like alphabetic order, in either in the reverse direction or in the other direction, and so on. Now this means that if it is doing in a breadth first order, then I need to put my trap file in a way so that in a breadth first order it comes first. But if unfortunately the ransomware is doing it in the depth first manner, then I have to put my trap file in a way so that it encounters the trap file faster in the depth first search. But if it is not doing either of them and doing alphabetic order, then I have to put my trap file with an A. But if I put it with an A and that ransomware is doing it in the reverse manner, then I am going to have to do it with a name with Z. So therefore, it is very difficult to create a generic place or generic set of places where the trap file has to be put. So this picture basically is showing you this. So what we did is that we created something called, we used something called affinity propagation with file name order heuristic. So basically it's a clustering based methods. So so we clustered the files based on file size, file type, creation and modification dates. And then in case the ransomware actually is encrypting in the random order, then it is best to have multiple trap files, one for each type of clusters. So we actually cluster the files based on these affinities. And then for each cluster, we have a trap file. And then we have some additional ones, like I will have a trap file with A in the beginning, a trap file with a Z in the beginning, both in every directory. So I'll have to basically decide using going into every directory and doing the clustering, and then having a cluster representation of files, trap files, and then I have to also add this additional trap files based on the file name order, and then I'll put enough trap files so that I have a high chance that no matter what kind of ransomware it is, it will fall into one of these trap files at the earliest possible. And then, of course, as I said, that we need a second corroboration, and that is done through the registry-based method, which could be a machine learning-based method or a rule-based method. So registry modification and so on. So this is what the RANDART is about, which is actually patented by my student. So here I have rendered works in two things. One is a file trap monitor, and another is a registry monitor. So if after the file trap monitor generates the alert, the process tree is suspended. Process tree involved in dealing with this trap. But then until I get the registry-based corroboration, I don't make the decision to kill the process. So once I have done that, then I will actually start killing the, terminate the ransomware process tree. So that's the idea. So this is the process termination module. And here we got a pretty good accuracy with a 99% accuracy, with precision also at a 99%, recall at 99%, and so on. So this was quite good. So now the detection delay, so we actually measured for various families that if I apply random, what is the detection delay? So we found that average detection delay came out to be 1.7 seconds. Now you see that for a couple of families, the detection delay was rather high. But most of them, you can see, is some of them are way below 1 second. Some of them are actually way below 2 seconds. Very few actually had longer delay, but at least one or two, like here you can see server, that one has a very high delay. And then here also you can see, I think it is Demonware that has also high delay. So, but you can see that Lockbit, Lawrence, Macop, Avadon, these guys are having a early registry modification. So registry monitor delay is about 1.6 seconds. A file trap is about 1.24. Now, as soon as the file trap monitors indicates, we actually suspend the process. So that basically means that this is the amount of time the ransomware got to actually do the encryption. After that, it cannot continue doing the encryption in 99% cases. So that saves us a lot of files. So average file loss we see is that about 70 files across 20 ransomware families. So file loss percentage average was about way below 1%. Right. Highest loss was observed in Babuk, Avos Locker, and Black Matter, as you can see here. So about 600 or so files here for below 500, etc. Because they use aggressive multi-threading techniques, so therefore, and they start working on different directories at the same time. So they do better with this. So Randart only raises an alert when both the file trap monitor and registry monitor will send signal to the decision module. So we also evaluated this for 15 days on regular machines. The reason is we wanted to see how many times the user by mistake falls into the trap. Because if the traps are too many, the user may also start interacting with the trap files, and thereby creating false alerts, and that would mean that this is not very good for use, because people will always get annoyed. But we at least in this 15 days we ran various things, but we did not flag any user activity as ransomware. So Randart successfully identified all modern ransomware variants that we worked with, averaging a file loss of about 0.35%, with a detection latency is about 1.7 seconds on an average. It uses minimal system resources, such as by running Randart in the background, does not have significant effect on memory or CPU or disk space, etc. And we also want to now look at whether data exfiltration only ransomware can be actually detected and stopped with the Randart. And this is the publications of my student who actually did all this work for his thesis. He just submitted his thesis, and he got his patent was Indian patent has already been approved, and another patent is US patent is pending on the last work. So that's the thing I wanted to talk about. Now, if you have any quick questions, I can take them.
So participants, I request video. So I request you, you all, if you have any query, you may ask, sir. You may put your question in the comment box. Comment box.
Yeah, so I think it's a 5-day FDP, right?
So, sir, it is 40 hours FDP, and it will mostly 8 days it will be taking.
I see. Okay.
Yes, sir.
So they will be also running, learning how to use sandboxes and
yes, sir.
and
Yes,
stuff
sir.
like
We
that.
have industry expert in those areas. We have invited them for this one. So, due to your busy schedule, I haven't asked for more times from you.
Yeah.
And it was very kind of from your side that you agreed to come for the session. Actually, initially I thought you won't be agree for the session, but just I tried
Yeah,
out.
no,
And
I am actually in Delhi today for a talk, so I have to rush to the CDOT,
yes.
but I had some time in the morning.
Okay, thank you so much, sir. So, sir,
Sure.
there are some questions in the chat box.
Yeah. So logbit can encrypt files. Does it depend on the file size? No, it doesn't depend on the file size. The order in which logbit encrypts may be dependent on the file size. It might, I don't know which one, what is the exact order, but it doesn't spare any file for based on file size. But usually most of them try to encrypt the large files first. Also, somebody asking for public available repository of well-known ransomware attack signatures. I don't know whether there are any public repositories, but any antivirus that you are using today would have signature of all these well-known ones, right? Like, Lockbit and all, if you're using Norton or McAfee or something, they should be able to have the signature. But the problem with the signature-based thing is that, as you will learn in this course also, that signatures are easy to vary and still have the same maliciousness, but signature will not match. So that is why a lot of other techniques are required, including this kind of dynamic techniques to detect. How we can identify direct system calls. So direct system calls also, you could actually create a feature set using direct system call also, right? Like for direct system calls are actually done through the this what is called IAT, right? So that is possible. Monitors were used. How does the detection of malware in real time? No, so hardware performance counted thing, as we saw, that we had to take the measurement up to 3 seconds or 2 seconds and so on. So after 2 seconds, now we get a 30, let's say 30 measurements. After 2 seconds, let's say I get 20 measurements every 100 millisecond. Then I have to actually push it to a decision module, which will be which would be a machine learning model. So that will add another another maybe a second. So in about 3 seconds, you might be able to have a 90% chance of detecting the ransomware. But in 3 seconds, you will have a lot of files encrypted. Can the malware in itself detect the traps, and how do we prevent this? Of course, malware or writers can actually know what is your trap selection method, and then they can do the reverse of that to avoid the traps, right? So that is possible. This is all a cat and mouse game. As soon as the malware authors detect the way you are detecting the malware, they will change their method. So it's none of this can last very long. It eventually they will figure out how you are putting the selecting the trap files, and then they will actually use the same method to actually know which ones are trap files, right? So can I use your trap file plus registry concept for ransomware detection in IoT devices? Yeah, so we have see the registry is a very Windows specific thing, so you won't have it in the regular IoT devices. So actually, my student also has done this for Linux. For Linux, he uses some other method for the corroboration. So trap file method is the same, but in Linux there is no registry, so there has to be some other method for corroboration. So that you have to figure out in what would be the one in IoT devices. What kind of IoT devices? How to deal with packed P files of ransomware in static analysis phase. Now, in in the method that I described in rendered, it packed and unpacked doesn't matter because we are detecting it after it is executing, right? So it will actually we are not doing any static analysis in rendered. So therefore, packed and unpacked won't matter. But you should experiment, right? These are very simple methods, so you can experiment and see. I mean, I don't know the answers, like how IoT devices, what would be your corroborating method and so on. But I think that should be done. All right. Which ML and DL algorithms are best for early detection and ransomware attack? Well, they're difficult to say, but what I found is that malware analysis, most of the time, tree-based, ensemble tree-based methods work well, right? Like so, random forest, most of the time we find in in malware detection of any kind, random forest does well, or other kind of maybe some ensemble method, but usually tree-based methods or similar methods work better. But nobody has actually given any proof that only tree-based methods work for this kind of data, and the other kind of like linear classifiers of this kind works for other kinds of data. I don't know of any such results, so I don't think you can say that for sure. But experimentally, anecdotally, I would say random forest type, or sometimes XGBoost or kind of thing also works.
Okay, so I think with this, there is no more question in the chat box. So we sincerely thank you, sir, for the
Sure.
insightful session. And the topic that you have discussed was literally those topics have set the tone for our program. Most of the concepts or terminologies that sir has discussed, like a static dynamic analysis, API calls, and someone has asked question about P file, obfuscated files. So these things we will be exploring in depth in future sessions. But definitely, this session was covering the ransomware in particular. But apart from that, it has also set the tone that how we are going to deal with those terminologies and how they are going to help us in malware analysis. So with this, thank you so much, sir, for your
Thank you.
time for us and giving us the opportunity to basically host you. Thank you so much, sir.
Sure.
And thank you
Thank
all
you.
the
Thank you.
participants. Uh,
Thank you.
thank you, sir.
Bye.
Bye, sir.
Have a good FDP.
Thank you, sir. Good day to you, sir. So, let me see. So, participants, so we